So, good evening. Thank you all for coming back for tonight. I hope you all had a wonderful first day so far. And please thank our gracious Austrian hosts for making this possible. I realized during the day that I forgot to do a very important thing this morning, and that's to ask all of you to give yourself a big round of applause for all the wonderful work you've done in the last few years since we saw each other. And yeah, pat yourself on the back, give yourself a big applause, just hurrah! So with that out of the way, please, Claudia.
Thank you, Claire. Welcome to all of you who made it through the rain and after the dinner and did, in fact, join us here. I would like to introduce, even though I do not dare introduce Florian to Vienna, because he's a local hero. He's been here for a while. He studied here in Vienna. He's very well known to the Viennese skeptics, to the German skeptics, and also the European skeptics all over, because he's been publishing about skeptical topics for quite a while now and on quite a lot of platforms. So if you did not stumble across Florian, he has a podcast. He has several outlets where he tells us about the skeptic. Can I say evangelium? Is that okay? And he has two books published that are unfortunately not yet available in English. However, I think he'd be open to talk about translations with whomever wants to translate. First one is called Coincidence, the Universe and You, The Science of Luck. And like I already translated the title for you, so you just have to go do the rest. And the other one is called Gravity is Not a Gut Feeling. So you think about this while you listen to Florian when he gives us his latest and most recent insights, and I wish you a very good time. And think about smart questions after a smart talk.
Thank you so much, and thanks for being here. Well, why can we trust in science, and can we trust in science? Well, we're here at a conference in a room full of science nerds, so I won't ask you whether you trust in science or not, because this would be a little bit of a selection bias, I think. Let's not do that. But I think we as skeptics, we as science fans or science nerds, we should also sit back sometimes and ask, well, actually, why do we believe in what we believe? Why do we trust in what we trust? Because, you know, taken at first glance, it is not at all obvious that we can really believe in scientific results. And it's not in us as human beings. I mean, evolution has not taught us to believe in science. We can all imagine maybe our ancestors some 100,000 years ago wandering around looking for food, and then maybe they settled down in the evening and used the pinnacle of technology and science back then, which was making fire. And then maybe there was some rustling noise in the bushes, and out came a saber-toothed tiger and grabbed one of those guys and dragged him away, and the others screamed and fled. And the next day, still shaken by this incident, they wandered around again, and in the evening again they sat there, and again they heard a rustling noise in the bushes. Well, what did they do? They jumped up and ran away. They didn't think about scientific evidence. And I don't know if there was one guy who said, okay, come on, I mean, I see your point here, but this was one instance yesterday. N equals 1 does not really make a good scientific argument, so what we have to do is we have to look for several hundred rustling noises in the bushes and correlate that with events of people being eaten by tigers, and then you get the picture. This guy, the first scientist, he was eaten. So trusting in science is not necessarily an evolutionary stable strategy. And everyone, whether or not we are scientists, have this evolution in us. That's quite natural. So what evolution gave us is some sort of a gut feeling. And I don't mean that in a bad way. When we say, well, we romanticize that sometimes and say, well, listen to your heart, yeah? And I just can feel it, what the truth is. We tend to ridicule that, but we shouldn't really, because this is valuable. Actually, we couldn't get through the day without that. We cannot always question everything scientifically. This is evolutionary heuristics for solving problems, and we should be grateful that we have that. However, we know that those feelings we might have are not particularly reliable. And we as humans, using our brains, using scientific methods, can go beyond that. And that's quite normal. I mean, we have eyes provided by evolution, and they work really well, but we have devices sometimes which actually make our eyes even better, and we can build microscopes and see things which our eyes never could. So it's quite normal to go beyond the capabilities that evolution endowed us with, and we can do the same with science to become smarter than we would be otherwise. But to me, an important question is, where is certainty, really? So what are those things that we can really be sure that they are true? And if you take a second and think about a statement that you personally are absolutely sure of, what would that be? Well, when I ask this question, many people come up with something from mathematics, something like, well, 2 + 2 is 4. I'm pretty much convinced that that is true. And there's a good reason for that. Mathematics is maybe the very basis of reliability. And this is several reasons. One is that mathematics is that which cannot be thought differently. So you can even use that as a definition of mathematics. Mathematics is the science of that which we cannot conceive differently. We cannot think of a world with a different kind of mathematics. I can think of a universe with a different kind of physics. I can visualize a universe without gravity. Then, okay, there would be no stars and no planets. There would just be rather boring atomic dust, but yeah, we can think about that. I mean, for that matter, I can think about a universe which consists purely of bright red cowboy boots. That would be a rather stupid universe, but I can picture it in my mind. However, I cannot picture a universe in which 2 + 7 is 24, or in which every triangle has 4 corners, or in which A is greater than B exactly when B is greater than A. That doesn't work. I cannot do that in my head. Mathematics is that which cannot be thought differently. And this has to do with the method of mathematics also. In mathematics, we have some beliefs which we consider to be self-evident, and we call those axioms. And from these axioms, we derive other statements. And this is a very old strategy, and it dates back all the way to this guy, Euclid of Alexandria in ancient Greece. Well, actually, Alexandria is today Egypt, but he spoke Greek and wrote in Greek, and he developed geometry of his time and wrote very important books. And back then, mathematics was pretty much geometry. And what he did was something quite beautiful, really. So he didn't just come up with theorems here and there, but he started at basic principles with definitions. Okay, you can't argue with a definition. Yeah? A point is that which has no parts. Yeah, okay. Nobody's going to argue with that. We just have a thought and we give it a name and call it point. That's fine. And then we can have axioms. Those are statements which help us do something. Yeah? For example, things that are equal to the same thing are also equal to one another. That's nice. So if the square on the left is as big as the square in the middle, and the square on the right is also as big as the square in the middle, that means that the square on the left is as big as the square on the right. Okay, nobody will argue with that. That's self-evident. So we are all convinced that this is true. We don't have to fight about that. And that way, Euclid came up with a number of axioms, and then you can say, okay, but that's trivial, that doesn't tell us anything. Yet, okay, but using those axioms, you can combine them to form more complicated statements, and then in just a few easy logical steps, Euclid arrives at something which is not trivial anymore, such as the theorem of Pythagoras. That directly follows from those very, very simple axioms. Okay, so that means if we believe in those very simple axioms, which we said nobody can argue with anyway, and if we believe in the logical steps that Euclid took, then we also have to believe in the result, which is the Pythagorean theorem, a triangle with a right angle, a squared plus b squared is c squared. Now we have to believe that. That's proof. That's mathematical proof. This has been expanded over the years, and in the 19th century there was an Italian mathematician, Giuseppe Peano, and he did a similar thing with numbers, and he came up with 5 axioms of number theory. You see them here written down in a rather modern and fancy way. Don't worry about the symbols. Those statements are incredibly easy. The first one is just 0 is a number. Yeah, okay. I can do that. I can say that. And the next one is every number has another number which is its successor. Okay, so you can always add 1. Yeah, that's also simple. And that way, step by step, you get the structure of numbers, and from that you can derive more complicated things, and you can go then to fractions and to different kinds of numbers and to vectors and matrices and to calculus and to all those nice and fruitful and complicated mathematics that you learned at school. And this was incredibly successful. So at the beginning of the 20th century, this was the big thing in mathematics. So mathematicians found out that it helps them a lot to really build this very, very solid foundations to come up with axioms and to derive everything, all of mathematics, from those simple statements using logical tools. And one of the guys who were particularly successful here was this man, Bertrand Russell, who together with Whitehead published the Principia Mathematica, a very famous book in which they tried precisely that, to derive all of known mathematics from very, very simple facts. And, well, maybe you could say he overdid it because he was very, very thorough. So he developed this logic notation with all those fancy symbols. And then, after some lengthy derivations, he says, from this preposition, it will follow that 1 + 1 is 2. Yeah, okay, I mean, we suspected as much already, but now we really know for sure. That's something, isn't it? Although, I mean, if you really want to look that up and study that, in the original version of his book, you need to go to page 379 until you get there. But then you know that 1 + 1 is 2, and then you can move on to all the fancy and more complicated mathematics. Now we really know for sure. And that way mathematicians could solve huge problems, which they could not have solved otherwise. And it was a big success. It was a great time for mathematics. And so there was, of course, the question, if it works so well in mathematics, if in mathematics we can build this huge palace of truth in which everything can be proved perfectly, undoubtedly, can we translate this method into other realms of science? And being here in Vienna today, I have to mention, of course, the Vienna Circle. The Vienna Circle was a club of people, mostly natural scientists, philosophers, also economists, and they discussed precisely those questions. How can we be sure about science? How can we do science in such a way that we can really prove our statements in a way similar to the mathematicians do it? That's a positivist view of science. And they tried a number of things. They were very much opposed to metaphysics, so I think those guys and us skeptics, we would have gotten along pretty well. But eventually, they had to realize that this project is doomed to fail. You cannot do that. You cannot really create science in the same way as you can create mathematics. You cannot prove things in science the same way as you can in mathematics. There are fundamental differences here, and even if you try very hard, it's not the same way of thinking. And there are several reasons for that. The first reason is, as I said before, mathematics is that which cannot be thought differently. So mathematics can be done purely in your head. But for all other sciences, you need something else. You need a universe. You need observation of some sort. And observation is a problem. Observation is always a little bit messy. And that always reminds me of William Buckland. He was a natural scientist, and this guy was known for tasting everything. And if you do geology, this actually may help you a lot sometimes. If you just lick a rock and then you know what rock it is. And he made a habit of that. And one day he was visiting an old church, and there was this legend then that in this church a saint had been killed in the Middle Ages. And since then, big miracle, there was this puddle of blood which appeared every morning again and again on the floor. And William Buckland went there, kneeled down and tasted it and said, nah, that's not blood, that's just bad urine. So William Buckland really tasted everything. But that always reminds me of the fact that, well, empiricism can be disgusting. You know, I'm a theorist, so I'm allowed to say that. Of course, not just because of that reason, because, you know, measurements are never perfect, and there can always be errors. There have to be errors always. So sometimes you maybe get data which is flawed. Sometimes you have to do statistics, and you cannot remove the errors altogether. Empiricism is always difficult, and it's never perfect, and we have to live with that when we do experiments. That's one problem. The other problem is the problem of induction. And this really bugged those guys in the Vienna Circle. This was one of the big philosophical problems at this time. So, a moment ago, we saw the structure of mathematics, where you start out with axioms and then logically you move on to other statements, to more special cases. Induction is the opposite. Induction means you observe special cases and then you come up with a general rule. So maybe you're an ornithologist and you study ravens and you watch lots and lots of ravens and you realize all of them are black, and so you come up with the rule, all ravens are black. That's induction. But of course, quite obviously, this is not a proof, at least not a proof in the mathematical sense, because, yeah, of course, logically, it is possible that tomorrow you find a raven which is not black, and then your rule was wrong. And maybe something crazy happens and all ravens tomorrow decide to be bright green. We don't know. We assume that this won't be the case, but we cannot be sure. So induction is never perfect. And this was really something those guys struggled with. And Bertrand Russell, the man who proved that 1 + 1 is 2, he said, well, if we cannot solve this problem of induction, then really there is no difference between sanity and insanity. So to them, this problem of induction was so deep that it put all of science in danger. And so this was really a main concern. Can we believe in anything? Can we believe in science at all if there is this problem of induction? And actually, this was a question which could not really be solved. And then came Karl Popper. And Karl Popper kind of turned this problem on its head. Karl Popper said, yeah, okay, induction is not perfect. And there's nothing we can do about that. We just have to accept that. So if we can't prove inductively, then let's not do that. Let's not pretend that this is the main objective of science. But there is something else we can do. Karl Popper realized that there was a fundamental asymmetry here, because even if you cannot prove that all ravens are black, even if you look at lots and lots and lots of ravens, you can prove that the statement all ravens are black is wrong just by looking at one single raven if it happens not to be black. So you can disprove the statements, but you cannot prove them. You can logically disprove all ravens are black by just looking at one raven that isn't, but the opposite is very hard. And that's why Karl Popper said, okay, if the one thing cannot be done, but the other thing can, well, then let's focus on the thing that can be done. Let's focus on disproving things and not on proving things. And that's why Karl Popper came up with his idea that the core element of science is not the possibility of a statement being proved perfectly, as it is in mathematics, but the possibility of the statement being falsified, disproved. And so he said it's the criterion, a statement is only scientific when it can in principle be disproved. That's the criterion of falsifiability. And that actually, I think, helps us a lot, because it draws a line, first of all, between statements which we consider scientific and statements which we cannot consider scientific. For example, I can say an electron has electric charge which is equal and opposite the electric charge of a proton. That's a scientific statement, because I can think of lots of experiments which could, in principle, disprove that. They won't, because the statement is pretty safe. We have tried that a lot of times. But I can conceive an experiment, and I can conceive a possible outcome of this experiment which would make me have to rethink this statement, which would make me admit that this statement was wrong. However, if I say my inner chakra is in cosmic resonance with intergalactic unicorns, then this is not a scientific statement. Why? Not because it's wrong, it doesn't matter at this point, but because it cannot be disproved. I cannot think of an experiment or an outcome of an experiment which would disprove that. I mean, okay, I can say, let's use the James Webb telescope and look for intergalactic unicorns. And then we won't find any, but that doesn't disprove anything, because I can still say, well, they are somewhere else, or they are invisible. I just can just feel those unicorns. Otherwise, they're not accessible by your puny human senses. No, okay, so a statement like that cannot be disproved, and that's why Karl Popper would say, okay, it's a priori not scientific, so don't worry about that, don't waste your time arguing with that, just dismiss it. And also, Popper's idea gives us, tells us how to do good science, or what distinguishes good science from not so good science. If you do good science, if you present a good theory, you should do it in such a way that if it is wrong, in case it's wrong, of course you hope that it's true, but you should present it in such a way that if it is wrong, it's easy to disprove it. So, you should not hide anything, you shouldn't present it in a wishy-washy way, such as maybe a politician would present a reform which is planned the next year or something like that. But you should present it in a very, very clear way so that it can be tested and so that it can, in principle, if it's wrong, be proven to be wrong. That's what you should do. And the question is now, well, does science really work like that? And the answer is, well, sort of. Not always, because nothing made by humans is ever perfect, but quite often it does work more or less that way. And a story which I personally like a lot is the story of the neutrino anomaly in 2011. This was a great experiment. It was a wonderful science story. Neutrinos are subatomic particles which don't do much. They just don't interact with atoms very much. So lots and lots of neutrinos fly through every one of us at this very moment, but we don't feel it because it just doesn't matter. It doesn't interact with us. Actually, those neutrinos can go through all of planet Earth without hitting anything. Of course, that means that they are pretty hard to detect, but that can be done if you have a really big particle detector, and such a detector exists in Gran Sasso in Italy, and there you can measure neutrinos. And you can also produce neutrinos if you do it right at the particle collider at CERN. You can collide particles in such a way that neutrinos are created. So, what people wanted to know is how fast are those neutrinos? So, they created those neutrinos in CERN, aimed the beam at Italy, Gran Sasso, and there they measured it. And of course, you can check the distance, and then you can do very precise time measurements and calculate the speed of the neutrinos. And what people expected was those neutrinos should be almost as fast as the speed of light. Because the speed of light, as we know, according to Einstein, is the upper speed limit for anything in the universe. And those neutrinos are really, really light. They have very little mass, and that's why they are usually very, very fast. Okay, so they did this measurement, and the result was those neutrinos were a little bit faster than the speed of light. And that's not good. That's not what you want. If you get a result and want to hand in your PhD thesis, then it's bad news if you break the laws of physics. Okay. Of course, they checked for errors, and they rechecked and triple-checked, and neutrinos were still faster than light. So what did they do? Did they hide anything? No, they did not. They published it. They didn't publish it by saying, "Ha, we broke physics, and everybody who thought that the speed of light was the maximum is stupid." No, they didn't do that. They said, "Okay, guys, we have found something really weird here. We know that it's probably wrong, but we checked this and this and that already. So, dear scientific community, help us check. What do you think? Maybe it's something interesting." And of course, lots of people, I just still remember those discussions back then, of course, lots of people came up with fancy ideas and were talking about additional dimensions and wormholes and stuff like that. Of course, everybody in the physics community assumed, well, probably it's just a mistake, but maybe it's an interesting mistake from which you can learn a lot. That happens. Unfortunately, it was not. It turned out to be a rather trivial mistake. It was just a faulty cable. And as soon as those guys took the cable out and plugged another cable in, then the neutrinos were a little bit slower than the speed of light, as you expect from well-behaved particles in this universe. Everything was nice. So unfortunately, no new physics coming out of this experiment. But I think it's very instructive to see how science works. There was this theory, neutrinos are faster than light, and it was put out there. And it was put out there not in some fancy esoteric way, but in a very clear-cut way, in such a way that it could be examined by other people and refuted by other people. And that's how science can make progress. And of course, this was just a rather flimsy statement, but sometimes, of course, one might even feel tempted to call a big scientific theory into question. And then, if a big theory is changed, there may be something we call a scientific revolution. And Thomas Kuhn, famous philosopher of science too, looked at the history of science, and to Thomas Kuhn, the history of science is a series of revolutions or paradigm shifts, as he said. So Kuhn said that we have some certain beliefs at some points in time, and they don't evolve gradually, but sometimes they shift massively. Just think, for example, of the shift from a geocentric view of the universe to a heliocentric view of the universe. First, people believed that the Earth was in the center, then people believed that the sun was in the center. That's not a slight tweak of your theory, that's a completely new theory. So that's really a paradigm shift. That's new physics, new science. And of course, when that happens, some people don't like that and still want to defend the old position, and then all kinds of fights break out, and Kuhn describes all of that. But in the end, the better theory wins. That's the idea. Okay, that's the idea. But is this really how science works? Is this really how we do science? I'm not quite sure. Of course, you can find historical examples for that, but you also can find cases where things worked out a bit differently. And one story which I find quite instructive is this one here. It dates back to the year 1846. And in 1846, one night, two people decided to find a planet. And that's something which doesn't happen very often. Yeah? You know, I mean, a couple of planets were known since ancient times. Then Uranus was discovered in the 18th century. Big thing. Of course, finding a new planet is something wonderful. And the equations of motion for planets was already well known. Isaac Newton had come up with his theory of gravity. And so the orbits of the planets could be calculated quite well. And people knew already that this works. And so when Uranus was discovered, of course, everybody calculated the orbit of Uranus and had a look at, well, whether the calculations agree with what you can see through the telescopes. And it turned out, well, it doesn't fit very well. So in the grand scheme of things, yes, Uranus behaves more or less like the equations given us by Isaac Newton tell us it should. But not quite. There were some weird distortions in the orbit of Uranus. And of course, people wondered what the reason could be. And one possible explanation was, well, maybe, just maybe, there is still another planet. A planet which is not known yet, but a planet which, through its gravity, influences Uranus in such a way that this strange, distorted orbit of Uranus can be explained. But people also knew that it's incredibly hard to find such a planet. Already Uranus is so far out that it's really hard. You need to be very lucky to see it using a telescope, at least using those telescopes back then. And the sky is big. To find such a small dot is really hard. So they knew it would be terribly hard to find this other unknown planet if it's there. But there was this guy in France called Urbain Le Verrier, a mathematician, and he said, well, okay, let's assume that's the correct reason. Let's assume that there is indeed this additional planet, and that's the cause for the strange orbit of Uranus. Well, then let's just calculate where this unknown planet would have to be in order to explain this weird orbit of Uranus. It's an incredibly difficult calculation, but Le Verrier did it, and he came up with a result, and he sent this result to Berlin, to this guy, Gottfried Galle, and said, I've done the calculations, a new planet should be here, maybe you would like to have a look. And that's what Galle and his assistant did, and they took the telescope and directed it at the direction in the sky that Le Verrier had calculated, and they found a couple of dots, and they cross-checked what they saw with the star map, and indeed, one of those dots they saw was not on the map. One of those dots they saw was not a star. One of those dots they saw did actually move a little bit. It was a planet, and today we call it Neptune. In one single night, the planet Neptune was found. Why? Because of mathematics. Because of a prediction by a guy in France, which was then checked by people in Germany. Okay, so now circling back to Karl Popper, how should we view this story? There are two ways of looking at it. The first way is saying it's a huge success for Popper's method and for science. What happened here? Well, okay, there was this theory about a new planet, and it was presented in such a way that it could be disproved. Yeah? So if they had not found it, then Leverrier would have had to admit that, okay, there is no planet, it was wrong. But they did find it, so everything great. So in that respect, you can say, hooray, Karl Popper, hooray, science, that's the way things are done, everything perfect, let's move on. But you can also look at it in a different way. If you take a very naive and oversimplistic Popper view, then you could say, okay, hold on. At first, we had Newton's theory of gravity, and we had this one planet, Uranus, which had a strange orbit which did not fit with Newton's theory of gravity. So should we not, at this point, have thrown out Newton? Is not the strange orbit of Uranus a good reason to say, well, then Newton was wrong? Then what we used to think about astronomy and celestial mechanics is just not true. And you see where the problem is here. Nobody would do that. Nobody would be ready to throw out a theory such as Newton's theory of gravity out of the window so fast. But why? What's really the mechanism here? What's the justification here? And, you know, as a student, when I think back to the first semester physics lab, then I remember everything going wrong back then. So first semester physics guys doing experiments, it's terrible. So if every experiment which went wrong back then would have been considered disproving a physical theory, then there would be nothing left of physics. Yeah? So we cannot do that. Yeah? So if an experiment doesn't fit with the theory, we cannot always throw out the theory and call it disproved. That's not something we can do. And nobody thought that would be a good idea to say, okay, goodbye, Mr. Newton, you are wrong, we don't believe that your theory is true anymore. And there was another very important philosopher of science, Imre Lakatos, who had a closer look at that. And his point was, those guys were absolutely correct not to throw out a theory too fast. And Imre Lakatos said, okay, we have to realize that a theory, a scientific theory, has different parts. So usually you have a core of the theory, which is something very solid and very reliable. The core ideas of a theory, those are ideas that have been checked many times. They agree very well with what we know about the universe already. And then there is some kind of a softer region around this core. And in this softer region, there are statements which we are willing to tweak. So in that case, I just told you about, the core of the theory would be Newton's law of gravity. We are pretty sure that this at least has something to do with the world. And then around that, there is a softer core with additional assumptions. One assumption being the number of planets that there are in our solar system. And we are willing to give up these assumptions, to tweak the theory in its softer shell in order to save the core. And that, says Imre Lakatos, is absolutely justified, and we should do that. That's a good thing to do. Okay, so, but now we talked a lot about theories that were disproved. We talked a lot about falsifying stuff. And this is really a huge topic in the philosophy of science. Those guys talked about how to get rid of statements which we consider to be wrong at some point. But to me, the question is science, is that really the core of science? So is this really what we do as scientists? And I think not really. So all of that is important, and this falsification principle is absolutely important, and we should use that. But I think it's not really the reason why we trust in science, and it's not really the reason why we like science. I mean, nobody goes into science and says, I want to become a scientist because then I can disprove other people. I can annoy other guys because I can tell them they're wrong. Well, maybe there are people like that, but I'm not sure they will have the greatest career in science. Experimental physicists or something like that, yeah. Yeah, exactly. And nobody goes home in the evening from the lab and says, I had a great day. Again, I came up with hypotheses which, given the appropriate empirical evidence, tomorrow could turn out to be completely useless. Yay! No, that's not what makes us excited about science. Of course, tearing down is important. Of course, disproving is absolutely valuable. But we also need to build up something. We ultimately want to create something. We want to find out something. We want to know how the universe works. And that's why we do science. And I think it's very important to look at that as well and to understand why this works and how this works. It's very crucial to look at theories which have been replaced by other theories. So what does it even mean when there is a paradigm shift, as Kuhn said? What does it even mean when one theory is replaced by another? And a wonderful example for that is those two people, Isaac Newton and Albert Einstein. Both those guys worked on gravity. That was their big topic. But they did it in a very, very different way. So Isaac Newton had this gravity force law describing any two objects in the universe, given their mass, have some force attracting them to each other. That's all great. But Einstein had a completely different theory of gravity. In Einstein's view, in Einstein's theory of relativity, there are 3 dimensions of space and 1 dimension of time, and it combines to a 4-dimensional space-time, and there are masses in it, and the space-time is warped, and then objects move in this warped space-time, and that's basically why the Earth moves around the sun. It's a little bit complicated, but it can be done. So we have 2 theories of gravity here. 2 very different theories of gravity. So which one is better? Well, in some sense, Einstein's theory is better. Why? Well, because it's more accurate. You can calculate the orbit of a planet with either of those 2 theories. And when you really look at that, especially if you look, for example, at the orbit of Mercury, then, Newton's equations fit pretty well, but Einstein's equations fit even better. So if you measure very closely, then Einstein fits better with the experiment. That's nice. Also, of course, there are extreme cases in which Newton doesn't work anymore at all. If you have objects moving close to the speed of light, then you get big problems with Newton. You need Einstein. If you have strange objects like black holes, then Newton cannot say anything about that. You need Einstein. So there are cases in which you definitely need Einstein's theory of relativity, and Newton is useless. But in most cases, both are equivalent. So to calculate how the moon moves or how an apple falls down from a tree, Newton is perfectly fine. And that's a very important thought. When a theory replaces another, like Einstein's theory of gravity replaced Newton's theory of gravity as the leading theory of gravity that we have as humans, that does not mean that the old theory is wrong. That does not mean that the old theory is useless. That does not mean that the old theory is disproved. It's still there, and it's still useful. And what's useful today will be useful tomorrow. And when we send rocket ships to the moon today, we calculate the trajectory not using Einstein's equations, but using Newton's equations. Why? Because it's much easier. It would be crazy difficult to do it with Einstein, and you can estimate that there would be no difference, no discernible difference. Yeah? The difference would be in the range of the error that you have for different reasons anyway. So it would make absolutely no sense to use Einstein for that if you have Newton. And that, I think, is a very crucial thought, because many people get that wrong, especially people who never had much contact with science. They say, well, okay, but scientific theories are all nice and well, but they get disproved all the time. So why should I trust you guys? Why should I believe scientists if we know from history that scientific theories, which all those fancy professors thought were true, are then disproven and refuted? Why should I believe in what you say today? That's something I've heard a lot of times. And the answer is because that's not what happens when a theory is disproved. Of course, simple statements, single experiments, single assumptions, measurements, that might be disproved in a way so that it's really gone forever. That happens. But a big theory, such as the theory of gravity that Newton came up with, a theory which has proven to be useful in many different contexts, such a theory, I would like to argue, is extremely stable, cannot be disproved. That sounds like a contradiction to Karl Popper, which I don't intend it to be. It's just different use of the word disproved. But a theory which has been shown to work will also work for the same problems tomorrow, even if another theory comes along, which might be better in some cases. And in that case, what we know about science today is extremely reliable. And I would like to argue that this does not only apply to theories like Newton's theory of gravity, but even to theories which we find a little bit ridiculous and which we consider completely disproved. Think, for example, about the theory of the flat Earth. Okay, we all know the Earth is not flat. We won't disagree on that. But when I walk around in Vienna and I think about whether or not I should turn right at the next crossroads, then I don't think about the curvature of the Earth. Then in my mind, the Earth is flat. Of course, because a sphere can be locally approximated by a plane, sure. And so in that situation, that's all I need. Of course, if I board a plane and go to New York, then things are different. Then I have to take curvature into account, for example, to determine the time difference, which is due to the curvature of the Earth. That's fine. But in some contexts, even something as ridiculous as believing in the Earth being flat makes sense, and we use it. And the same is true for the geocentric model. Of course, I know that the Earth rotates and rotates around the sun. But when I'm at the beach and I want to know where to place my sunshade so that the shadow travels in the direction where I have my seat in the sand, then I think, well, where would the sun move? And you see what's happening here. Yeah? I think of the sun as something that moves. That, in this case, is the correct working hypothesis. Thinking, well, in which way does the Earth rotate so that the apparent position of the sun... No, that's rubbish. That's much more complicated. So it's a part of science to use the appropriate working hypothesis, which is suitable for the situation you're in. It's not the job of science to find the ultimate truth, it's the job of science to be useful. And even theories which are pretty ridiculous, such as this, is useful in our brains still. And the question is, what theories qualify for that? What theories are good enough to survive that way, even if better theories come along? And I think the main ingredient for really the trustworthiness of science is its net structure. And that's very, very different from mathematics, as we talked about before. So science is this huge net of many, many different observations, experiments, calculations, assumptions which are backed up by other observations and experiments. And there is usually not this one experiment which proves that something is true, but there is this bunch, this net of interconnecting empiric pieces of evidence. And that's what makes science so strong. And that's very different from mathematics, because in mathematics, we have those completely unbreakable links between one statement and the next. And if you find a logical error there, then it's gone. But in the natural sciences, it's different. There you have this web, this interconnected, thickly woven web of observations, of facts, of hints. And if one thread breaks in this net, it doesn't matter. So if you realize that there was an error somewhere, yeah, okay, don't worry about that, because we have 78 different ways of building this argument that this theory of gravity, for instance, is true. And that is what makes, in my mind, science so trustworthy. It's about converging evidence. It's about having different ways of getting there, which kind of tell the same story. And if and only if this is the case, then a scientific theory is something you can trust in, not to be the ultimate truth, because, yeah, who knows the ultimate truth, but to be something historically stable. And I'm really absolutely convinced that if science progresses for another couple of centuries, which I do hope very much, then in 500 years from now, people will not look back at our day and say, look what those simpletons believed in. No, they won't. Of course, they hopefully will have theories which go far beyond what we know today. But our quantum physics, our classical mechanics, the stuff that we use today, will still be in high regard. It will still be a tool which is absolutely useful for many applications. Maybe then people will have different machines which require different theories. Fine. But for many applications, today's physics will absolutely be enough. So I think we should view science as an emergent phenomenon, really. An emergent phenomenon is something which cannot be explained just by looking at its parts. And that's something ubiquitous, really, in this world. So there are many examples. Water being wet, for instance. We won't have to argue that water can be wet. Yes, it can. But water is just H2O molecules. And can an H2O molecule be wet? No, not really. The term wet just does not apply to H2O molecules. Of course, you can think about intermolecular forces and what wetness requires in terms of those intermolecular forces and whatnot, but no, that's not wetness. We can only talk about something being wet if there's a lot of molecules, and then we can discuss, well, do they form a crystal, or do they form a liquid, or is it vapor maybe? Then different terms, different ideas come into play, which just don't make sense at the level of the molecule. And this is true for many cases. It's also true for your brain. Your brain has thoughts. Yes, there is no arguing with that. But your brain is also just a collection of neurons. And no brain cell has ever had a thought. No, the word thought does not apply to what brain cells do. That doesn't work, because a thought depends on many brain cells firing in some electric pattern, which is in some way coherent. Yeah, we can go deep into that. But thinking is an emergent quality of brain cells, and the term only makes sense when there's a lot of those. So if you add a lot of brain cells, then something new happens. And I think the same is true for science. When we have a lot of evidence, a lot of ideas, a lot of measurements, a lot of experiments, a lot of calculations and computer simulations, and this all goes together in a coherent way, then something new happens. Something new happens which cannot be explained on the level of the single logical argument. And this something new which comes out of this mass of evidence, this is the trustworthiness of science. So in that sense, this is very different from how mathematics is done, where one proof is enough. But everywhere else in science, we have this net of evidence, and that's what makes science so strong. And this is also the reason why science is also a social phenomenon, because this tightly woven net of empirical evidence and theories can never be provided by one single person. It's just too big. Science doesn't fit into a human brain. Even the brightest among us cannot do that. And so science is created not like a piece of art is created, but it's rather created like ants create the anthill. So there is no boss ant. There is no ant which has figured out the plan for the anthill. No, they don't know. They have no idea what they're doing. They just walk around and drag along some nails in the wood and build up those weird structures with all kinds of inner walkways and paths and chambers and whatnot. And in the end, that way, without really knowing what they're doing, they create something which is beneficial for all the ants. And with science, it's the same. There is no president of science, and there never will be. And to be honest, scientists don't really know what they are doing most of the time. But for some magical reason, it all comes together and forms something which has structure and which in the end is beneficial for everybody. And to me, this is maybe the most amazing property of science that there is. And I would like to end with pointing out that it's not only scientists who work as those little ants building up the big anthill of science, but it's every one of us. Because you cannot really, in a modern society, draw this dividing line between scientists and non-scientists. That doesn't work. Of course, somebody who does experiments in the lab every day contributes more to science than the average person. Yes, sure. But science is a product of a complex society. And every one of us, as we talk about science, as we use technology, as we discuss politics connected to science, and large portions of politics are, as we do all that, we contribute to science in some way. Because it's not just about the experiments, it's not just about the theories, it's about this interconnected web of people which creates this interconnected web of evidence, of facts, of theories which all fit together. And in that sense, I think we can all take pride in the fact that we are part of this big net, that we're part of science, and we can all together be proud of what science has accomplished. Thank you.
Thank you, Florian, for the perfect timing. I see 3 hand signs over there and 1 here in the front. And okay, so please, number 1 here, number 2 here, and number 3 here. And then if you, yeah, I see you too. Number 4 is down here. So I remember you, but everybody else, like, wait until we have this round done and we have 15 minutes for discussions, please.
This is probably just a quick question. Are you the one who made those drawings?
Yes.
Good job.
Thank you. Yeah. The reason is just that I don't want to get into trouble with copyright infringement. That's why I just draw everything myself. By the way, if you're interested in this topic, this is my recent book, as you've already mentioned. Thanks for that. It's available at the moment in German and in Korean for some reason. So, yeah, if you're a publisher, know a publisher, and think that it might be interesting for audiences in other languages, happy to talk to you. Yeah, okay. Let's take the next question.
So, okay, working. So first I would have addition to the mathematics part that we're talking about, then,
Yes.
then a question, if that's fine. So you were mentioning the work of Russell, his positivist idea of building up all mathematics from a set of axioms. But I think the very important point here to mention is Gödel's incompleteness theorem, which completely threw out all of Russell's attempts, because he showed first for Russell's Principia Mathematica that there are statements in Principia Mathematica that are true but cannot be proven, and then later he showed in general that in any kind of system of axioms there are true statements that can be proven. So that kind of completely ruined this positivist idea, even in mathematics, not just in science. So that was my point. And my question is, which is unrelated, is how should we deal with certain branches of theoretical physics which kind of fail this falsifiability criterion, like multiverse theories, etc., that make predictions that can't really be falsified? Should we treat them as pseudoscience? Should we treat them as a branch of mathematics? Or how should we deal with those kind of theoretical physics?
Thanks for that. I think those were two very, very important points. First, Gödel's incompleteness theorem. Yes, there is a whole big chapter on that in the book, and I just didn't have time to cover that. That's very true. So this big dream of mathematics in the beginning of the 20th century was actually to have some machine, some mathematical way of finding out for each and every possible mathematical statement whether it's true or false. And that cannot be done. And that's what Gödel showed, that mathematics cannot be complete in that way. That's a very important thing, and you're right. When you talk about axiomatic mathematics, that's the big point where everything breaks. However, that does not mean that mathematics is in any way unreliable. So if we get to mathematical truths, there are still unshakable truths. Gödel just said there might be truths which are true but cannot be proven. That's the point of Gödel. The second point, the question, very important question: how should we view theoretical physics or branches of theoretical physics which do not even attempt to be falsifiable, which do not even attempt to say something which can be tested in an experiment? And I think we should treat them as a pretty interesting form of art. So I like that. I think we should have people thinking about multiverses, but I don't want to be one of them, to be honest. So it's a bit difficult. For example, so many people talk about string theory when it comes to this topic. And I think it's a little bit unfair to say string theory is something like that, something which is completely detached from the world. No, it's not, because of course string theorists have this idea, this dream of coming up with results one day which can then be tested. That's the idea, and in that sense it's valid. But you're absolutely correct. There are papers being published about, well, weird ways how the universe could have begun. You find that in newspaper headlines then every few months. No, now it turns out there is no Big Bang, but in fact we are living in the inside of a black hole. That is no link whatsoever to empiricism, and that's why I find it not very interesting. I think people should do that, but it's more an art than a science.
I think I didn't understand well the question, but I think I wanted to ask the same thing about Gödel, so you answer already. Okay. But in fact, mathematics are not so strong, they need to be strong defined, but practically in the 18th and 19th century, mathematics were very well developed by famous mathematicians like Euler, Lagrange, and Gauss, and so forth, without everything being proven on strong axioms. So there's also a little freedom in it.
That's true. That's true. So even before this attempt to base everything on those axiomatic foundations, there was great mathematics, of course. And the structure of what those people did before that was basically the same. So still there was this going from one statement to the next logically that's inherent in mathematics. They just didn't build it all the way up to the first principles. Of course, you can do mathematics doing that. But there were some problems. So back then, at the beginning of the 20th century, infinities were a big thing, yeah? Because people did not know how to deal with infinities, and they had some problems. And that, for example, was a field which profited tremendously from this very rigorous axiomatic approach, and those problems probably, I guess, could not have been solved otherwise. But there is lots of mathematics you can still do, you're right.
So the fourth question was retracted. As I see, we have 6 more minutes for questions. Please, Stefan, and then, or the other way around. And then Stefan, you go next.
Well, in the morning we had discussed homeopathy in some issues, and I think also homeopaths can trust in science, but the problem is they only can trust in science when they use their mobile phones.
When they use what?
Their mobile phones, because in the mobile phones there's a huge amount of science.
Could be magic.
That's true. So the existence of technology and the fact that technology most of the time works really well is, of course, a great big argument that there is something there. So this net of science and evidence does not dangle from nothing. We see every day that it's connected to something which is true. And yeah, every bit of technology shows us that, sure.
Florian.
Yeah.
You know that founder of our Viennese Skeptic Society, Hans Oberhummer, was a proponent of panspermia theory. Do you think that panspermia is a scientific theory?
I do think so.
Can it be disproven?
Well, can it be? No. Actually, that's a good question. Look, I think, no, probably it does not qualify as a falsifiable theory. However, I think it's fair to present thoughts which are perhaps not meant to be a theory. I think sometimes that's okay. Just as before I said, sometimes it's okay to think about alternate universes and parallel dimensions and whatever, but I wouldn't really call it science. Maybe this is something similar. I think it's okay and it's absolutely valid to think about that and even to write papers about that and publish that. But of course, at least you should come up with some empirical evidence which is connected to it, not empirical evidence for this statement per se, because probably it doesn't exist, but just connected somehow to this web that we have. I think that would be my wish.
So I have one question here in the back, and then I have Lars, and then I have the gentleman in the front. So I see you all, but you have to give me some time to direct the microphones to you.
As you mentioned, the web of evidence, do you think that the scientists, when they are in this net of evidence, know all the pathways belong to their theory?
No.
So, or is it something that is more in the retrospective?
No, I think every scientist just has a local view of this net. And that's the amazing thing about science, that you cannot overlook this net as a whole. Nobody can. But humanity can. So no human being can do that. But we, as a society, we as humanity, for some weird reason, we can. Of course, you know, you have this net with all those interconnections, and you as a scientist sit at some knot in this net. And you should check where the connections running all up to your knot, where they come from, and maybe even the neighboring ones. But then at some point you have to stop. You cannot look at the net as a whole. But if we work together, we can make sure that every one of those threads has been pulled and pinched at some point. And if that can be assured, then I'm happy to jump into this net and be confident that it will carry me.
Yeah, I would like to know, within the framework of this talk, is there still room for Lamarck's theory on like evolution? Because like we can say that our current understanding of evolution works in this way better, but as you said, it's not directly disproven, but the theory doesn't really work. So for you, is it a disproven... Sorry?
Which theory does not work? Lamarck's theory?
Lamarck's. So
yeah, but I mean,
is it disproven or does it still have value, in your opinion?
I'm not an evolutionary biologist. There are people in this room much more qualified to answer this question than I am. But I think you can definitely come up with experiments, and those experiments have been done, in which you test whether or not Lamarck's theory is right. And as far as I know, they were not very successful. I know that there are some experiments which have been claimed to show that this Lamarckist view is right, and then people have huge fights about whether or not this is true and where people went wrong. And actually, I think interesting books could be written, probably have been written on that topic. But I view it, and please correct me if I'm wrong, as a theory which is falsifiable. So it obeys this criterion, but I think has been falsified mostly.
Last question.
I remember as a child, I was very curious, and probably curiosity should be very encouraged amongst children. The other point is that, don't you think people should be, and it's difference between a non-scientist and a scientist, involved in the questions of how rather than why?
So the distinction between scientists and non-scientists, you say, is how and not
how
why.
And not why.
I don't quite understand. I think I get the how part, and I completely agree with because we're talking about methods when we talk about science. I'm not sure I understand what you mean with the why.
Just to admit, there is no predetermination.
Predetermination for what?
For anything. Things have no sense, and the answer to why is always hypothetical.
Yes. In many cases, I guess, the question why may take you out of the realm of science. And explaining what science really is of course, very, very closely connected to the question how. How did something happen? And also, how do we know that? And how do we do science? Yes, I agree.
Thank you again, Florian.
Thank you.
For all of you who are still here, whether you're going to have some or several glasses of something cheerful now and continue with the talks, or you go back to your hotel rooms or your homes, I'd love to see you tomorrow again, 9:15. We will start again. Then you will see and hear Massimo Pigliucci, who will be talking to us about skepticism as a way of life. So if you already want to prepare some of your questions for then, feel free to do it overnight. And I wish you a very nice evening and see you again tomorrow.